Okay, expectations. No prior, since this is a basic course, you're not required to know anything about statistics before you walk in here. I'm assuming that you've never taken a statistics course before, or if you have, you've taken it 25 years ago and have no clue what remember at all what you took then. Okay, that was my situation. I came back to school for a master's degree in I guess it was like the late 80s or something like that. And I had been away from school, I guess, for 20 years. I came up here because I basically was a chemist really more than anything else. I worked in water treatment. We did most of our work in large office buildings and facilities, hospitals, and so on and so forth in the New York City area. And at that time, early 80s, mid 80s, late 80s, indoor air quality was becoming a big concern. We have a lot of clients that didn't know to call about indoor air quality. It was a completely new field at the time. So they started calling us because they knew we were chemists and we were as close to anybody that they knew that might be able to help them. And we decided, gee, we need to hire someone that knows something about this stuff. We did it for a while for ourselves without knowing anything, and that worked out okay, but not great. And so we need to hire somebody. So I came up here and to post a notice for an EOHS person, maybe a recent graduate or someone that's almost finished with the program for a job. And I went into Dave Cuttle. I went into what Diane Browse's predecessor and told her I have this notice I'd like to post. And she said, well, you got to get it approved by the head of the department, Dave Cuttlechuck. I went into his office. His office was like just stacked high with papers. He was like one of these jungles. He was kind of a hoarder. You'd have to go through corridors of paper and find him way in the back of his desk. And I asked him, would you allow me to post this on the board? We're looking for a recent graduate. We're interested in doing this kind of work and so on and so forth. He told me, oh, we have some great people. They'll be perfect for you, so on and so forth. If there's any other thing, I'll be glad to initial this and you'll be able to put it on the board there. I'm sure you'll get calls. And I started to leave, walk out through the corridor of papers. I started to leave. He says, oh, Tony, hang on a second. Let's have a chat. Sit down and talk to me for a few minutes. So what's your background? Where'd you go to school? So we had a chat, and he knew some of the professors that I had had 20 years before that, 20 or 25 years before that. Brooklyn, I went to Brooklyn Poly, and which is now NYU or something like that. I don't even know what they call it these days. Um, City, yes, it's Metro Tech or something like that. So I don't know. Yeah, it's got some weird name. But at any rate, so we chatted for a little while. He says, I'm teaching this course, Chemistry and Physics of the Environment. You would love this course. Back then, believe it or not, back then it was really cheap to go here, right? In the 80s. It was like, I think $35 a credit for graduate school. Back in those, it was $35 a credit. And so he said, it's cheap. It's really a great course, really interesting material, this, that, and the other thing, so on and so forth. You'd love this. So he says, well, I asked him, what do you have to do? Well, I'm an advisor. I fill out this paper, put you in the course, and you just go to the bursar and, give him a check or something like that, and you're in. So fine. So wow, that's pretty interesting. So I walked out and went up there to post the notice. And I walked out registered for 3 graduates. I hadn't been to college. I hadn't been to school in 20 years or 25 years. I don't even get out of the office. He stops me again. He says, Tony, I'm teaching another course in that same room. We wouldn't have to get up even. I'll sign you up for that course too. I'm registered for 6 credits. I showed up to put a piece of paper on the wall. That's the kind of guy that this guy was. He was a great teacher. But so at any rate, that's how I got into this. And I was in exactly that situation. Right now, I was very good in chemistry and math, so I didn't have much problem with this stuff and the EOHS stuff and stuff like that. And I was taking course back in those days. There were a lot of nursing students in the coursework here. They were down at Brookdale at the time, which has a big nursing school, so a lot of them would cross over into EOHS and some of the other coursework and public health and stuff. So, and I always had a crowd around me before class, because I knew the math and I knew the statistics and so on and so forth. And I was feeling pretty sure of myself and stuff like that. And until about maybe, about 3 or 4 or 5 semesters in, I took toxicology and they buried me. I had no idea. I had never taken physiology or any of that stuff. I didn't know anything about the liver. I hadn't looked. I work with water, which is basically physical chemistry. I hadn't looked at organic chemistry in years. Yeah. So I was completely lost. So they rescued me there. You know, they got a chance to help me out. So at any rate, so I know it's challenging. I know that this is new to a lot of you, that this is a math course, and a lot of people have phobias about math. So we're going to try and make it comfortable for you. The starting point is nobody knows anything about math in this course. Okay, and we'll work from there. I told you about the exams, the end of term project, and try and keep up with the homeworks. Learning objective. We're going to look at SPSS. We're going to look at Excel. Those are specific kinds of software that we're going to be actually using this semester that you guys are going to have to learn some skills with. So it's not just using math, but you really got to learn a little bit about this software. SPSS will serve you in the future if you're getting involved in actually doing some work that involves statistical analysis. Excel will serve you everywhere. You can use it in engineering, you can use it in science, chemistry, in finance, in statistics. It has so many uses. It's ridiculous. It's really something that's not just a statistics skill, but a life skill. So if you haven't, how many of you are really comfortable with Excel? Use it a lot, really comfortable. That's a good portion of the class, maybe about 60% of the class. I assume the other 40% probably don't get to use it very much, but it's really an important skill because you can use it in a lot of places. Tonight main thing we're gonna start talking about is how to just get acquainted with this software, and maybe in terms of statistics, talking about data and how we can describe data and the kinds of data that we're going to be talking about. In this case, we're talking about the types of data. We're going to get to that in a second. Syllabus, this is the couple of the options. Recommended textbook. There's also an alternative textbook, a little bit cheaper, that's available print on demand that might be interesting to you, and a website that has kind of an online textbook as well. Okay, so we're going to talk about statistics from a number of points of view. First of all, part of statistics is planning. I'm going to go out and I'm going to gather information. You want that information to be useful to you later on, right? So you have to do some planning in terms of how am I going to collect that data? How am I going to record that data? You want to know how to describe that data. And then you're going to make inferences based on that data. We're going to learn each one of these steps. I have a PDF of this. This is a timeline of statistics. The main point that this gives you is that statistics is not new. I mean, long before people knew it as statistics, people were collecting data, analyzing data. Levi focused on this use of an average, first use that recorded use that anybody knows about, of the use of taking an average of something and using that information to make a prediction, right? So 450 BC we're talking about goes pretty far back, and you'll see that there's been developments over many years. Some of these names, and you can look at this PDF file and kind of blow it up when you look at it in Adobe Acrobat Reader and actually read a lot of this stuff. I know it's impossible here. And a lot of these names and pictures will be meaningful to you by the end of the semester. There'll be things that, oh, well, yeah, that's when they talk about teacher, the t-test, teacher's t-test. You'll know who they're talking about. When you talk about Pascal, we'll have a rough idea who that guy is, Pascal. Okay, so some of those things will mean something to us. First of all, let's talk about, we'll begin with a couple of definitions. First definition, parameter and statistic. Okay, a parameter represents an entire population. Okay, so if I were to tell you that let's see, the average age of all women in the United States is 47.3 years old. What is that? Is that a parameter or a statistic? It's a parameter because it represents the whole population. Okay. If I were to tell you that we took a sample of 500 women, 10 from each state in the union, and we got an average of 46.3 years old, what's that? That's a statistic. Okay. Anything that involves a population is called a parameter. Anything that involves a sample from a population is a statistic. So we're going to be using that quite a bit. So all people in the world is a parameter. American adults is a parameter. Residents of New York is a parameter because I'm talking about all the residents. But if I'm talking about a sample of residents of New York, then we're talking about statistics. Okay, I'm going to skip through that. Okay, any place, let me go back. Any place, on a practical basis, we're almost always dealing with statistics, right? Because it's not practical. If I wanted to know what the rate of diabetes was in the United States, right? Or let's say United States, the rate of diabetes among graduate students in Hunter, right? One way for me to do this would be to go around and survey or test every Hunter graduate student. And then I know a parameter. I know the rate of diabetes in Hunter graduate students. That's usually not practical. What we do instead is we randomly sample those students and we try and guess at the rate in the population by determining the average for that sample that we took. Okay, so now, anybody think of somewhere where we actually sample an entire population? Did that ever happen? What's that? How's that? Oh, no kidding, really? Wow, how did they do that? How did they do that? Yeah.
You're talking about medical records. Because they each have their own little card.
Oh, wow.
Around.
Like a medical ID? Yeah.
Every doctor, you just swipe the card and you have the whole.
Yeah, yeah.
So they could probably do that in South Carolina.
Okay. Well, we do it here in the United States. We do it here in the United States. We take a census every 10 years, right? So every 10 years, a census, according to the Constitution, has to be a physical count. Okay. Now, in New York City, right, there are a lot of Hispanics, for instance, that are undercounted. Why are they undercounted? Some of them may not be legal, right? So they're living in New York City, they're using resources in New York City, but they're not counted in the census. Well, that's pretty easy to fix, right? You could go in and probably figure out what percentage of Hispanics are actually responding to the census, what percentage are, and correcting. Is there a reason why they don't correct it? I mean, we've got statistical tools that we could use to make it more accurate. Why wouldn't they do that? Anybody know why they don't correct the census when they know it's wrong? It's undercounting or something like that? Not money. Not in this case. Maybe politics, but not money. It's in the Constitution. Constitution says it's got to be a physical count. Can't be corrected statistically. Got to be an actual physical count, right? So in order to correct the census for known undercounts or overcounts, you'd have to pass a constitutional amendment. When was the last constitutional amendment passed? I don't remember. Hasn't been enough cooperation politically in this country to consider any constitutional amendment. The closest I can remember recently was the what was it? The Equal Rights Amendment. And that failed. I think there were 2 more states that had to ratify within the amount of time required for that to pass, and that must have been late 70s, something like that. There hasn't been a constitutional amendment since then. So not that easy to change. So a census in the United States is an actual count. Okay, and it counts how many people there are, how many children, how family sizes, a lot more information. They do count some more stuff. There's some basic stuff that's part of that physical count. They also focus on some families. Anybody here ever get picked out for that more detailed count where they send you like an 8-page or a 12-page form and you got to give them all, you voluntarily, I guess, give them all so the extra information about your insurance status and so on and so forth. Nobody in here at all. Somebody at work where I work was picked out. You fill out this extra form. They hand that out randomly. They get results from that, and that's what they use for their various statistical analyses of how many people, when you hear that, 10% of the population is uninsured or 15% now, that's what they're using for those statistics. It's not really part of the original census, but it's kind of a follow-up study that's separate from it. Nobody's judging apportionment, political stuff on it or anything like that, or handing out money based on it. Okay, you can go online right now and get the New York City morbidity or mortality report for each year. I think the most recent one that's available is 2013. I guess 2012. Probably not 2013 yet. They're probably still assembling. Maybe 2012, and that will give you a graph like this. That will give you the mortality rate in New York. You know, if you look at this closely, you can see like when it went up and when it went down, and some of the reasons, cholera outbreaks, and so on and so forth. That last big tick up was the post World War One influenza outbreak, and so on and so forth. And it's been gradually declining over time. If this continued on, you see even more of a decline. But you can actually go online to go to newyorkcity.gov and ask for the morbidity and mortality report. Just Google for it or search the site for it, and you'll actually find this information. And inside this booklet, behind this chart, you'll get all sorts of information. What people died from. What did they die from? Influenza? Did they die from heart disease? And so on and so forth. We're actually going to dig into some of that information later on. Okay, this is a rate. In other words, number of people per some number, 100,000. In this case, it's the deaths per thousand population in New York City. Okay, for each one of these years that we're looking at. Okay, that's a rate. Usually, when I say a rate, it means one thing divided by another. So it's deaths per thousand population. Okay, so we make the whole point of taking samples and doing statistics is not because we want to know about that sample, because we want to make inferences from that sample on the general population or on the population that we're interested in working with. In a political poll, you want to know who's winning, right? So you take a sample. You don't sample everybody, but you take a sample of it, and the inference from that is that if De Blasio got 40% of the vote in the mayoral contest in a poll, well, you think that means he's also going to get 40% in the general election when it happens. In fact, I guess this was probably the primary or something like that, right? Okay. And some of the things that we're interested in is how sure can we be of that number? What's the uncertainty about that number? In other words, we take a poll, says 40%, but what is the real population? Does that mean that I'm really sure it's 40%, or it could be 35 just as easily, it could be 55 or something like that? We want to quantify what our certainty is. We're going to be doing a lot of that as we go along. Anybody ever hear of the confidence interval? Okay, anybody know a definition of a confidence interval? Right? Can somebody give me a definition of a confidence interval? Mayor De Blasio, in this study, De Blasio has 40% of the vote in the sample that we took. What's a confidence interval? Confidence interval may be something like we're 95% certain that De Blasio has between 38 and 42% of the vote in the general population. So now I just don't have a sample of the population that says, oh, we think it's around 40% or something like that. Now I have an idea of what my level of certainty is. So confidence intervals and other tools that we're going to use to determine our level of certainty are important to us because they help us understand how accurate that number is likely to be. Okay, let's see. Okay. Okay, we're going to be doing studies that are experimental studies. We may want to determine how effective a certain intervention is into disease or a condition or something like that. It could be a lot of different kinds of interventions, like for instance, let's say the rate of injuries associated with cycling gone up since we started the city bike program, right? That'd be an interesting study to do, wouldn't it? Maybe that's a good project at the end of the semester if we can find data on that stuff, right? Has the rate of injuries gone up? Well, we may be able to find out about every injury, but then we have to guess at the number of people that's cycling. Are they cycling more miles and so on and so forth, longer and so on and so forth in different conditions? A lot of things that might affect that. Is one neighborhood more prone to asthma than another neighborhood is? Well, but it'd be difficult to to survey everybody in all these neighborhoods, but we could certainly maybe take a sample from each neighborhood. But we'd want to know how certain that number is. In other words, if Brooklyn, the rate of asthma is 10% and the Bronx is 12%, well, if the uncertainty in the Bronx is the confidence interval that we have in the Bronx is that we're pretty sure it's between 5 and 20%, and in Brooklyn it's between 7 and 15%. Well, gee, we're really not sure they're different there, right? So we want a handle on what our level of certainty is. That's an important part of the statistics we're going to be working with. Okay, for tonight, the main issue for tonight, that's an introduction into what we're going to be learning about statistics in the future. Our main interest in tonight, as far as data is concerned, is understanding how we classify data. Okay, we're going to classify data into basically three categories. You see four up here, but that's kind of a cheat because two of them are kind of the same thing. One of them is nominal data. Nominal data is basically a name, nominal name, right? So hair color is nominal data. Eye color is nominal data. Gender is nominal data. Anybody else come up with a nominal data? Occupation is nominal data. You know, you fit into a certain category, a named category. Sometimes you will call that categorical data. Okay, you'll see that name used kind of interchangeable. Nominal data, categorical data, it's categories, right? Next thing that I'm going to skip over ordinal data for a moment. The next thing that we're going to look at is numerical data, things that are numbers, blood pressure, weight, IQ, blood lead levels. What are blood levels in children? Blood lead levels, I think, are micrograms per deciliter, right? That's a number, right? Those are the units of it, but it's basically a number. We're going to separate those two into two types of numerical data. Discrete data, basically that's just integers. Okay, how many siblings do you have? Three, right? You're not going to say 3.5, right? Because you either have one or you don't have one, right? How many? Let's see. Let me think about this. How many cigarettes you smoke in a day? Right. That's a discrete data. I suppose you could say 3.5, right? That's kind of cheating, but yeah. We're talking how many entire cigarettes you smoke in a day, right? That's discrete data. Continuous data usually is things that are on a continuous scale. For instance, you can measure blood pressure in, I guess was it millimeters of mercury, right? And you could measure it at, 90 or 90.3 or 90.31 and so on and so forth. It's on a continuous scale. Both of those are numerical data. They're both numbers. Okay, continuous data usually includes decimals, and discrete data usually just means just a individual count or an integer. The third kind of data is ordinal data. That has order. It's kind of nominal data. It's kind of a crossover between the two. It's ordinal data. It's nominal data, but it has a rank, an order. For instance, if you were to rate this class at the end of the semester, you might rate it on a scale of poor, fair, good, and excellent. Right? Now, those are four categories, but they have an intuitive rank. Right? Excellent is better than good. Good is better than fair. Fair is better than poor. Right? So there's an order to that. If we assign numbers to it, for instance, your grading system, you could get an A, a B, a C, or a D. We could assign a number to that. A is 4, 3, 2, 1, and so on and so forth. It's got an order. Well, it doesn't necessarily mean, another example of that is pain scale. How much pain are you in right now? Well, let's say you're in statistics, it's the summer, so you're probably an 8 or a 9 right now, I'd probably guess. Right? We're still early in the class. Maybe we're at 7. Wait an hour. You'll be at a 9. Right? So you might say you're a 7. Okay, somebody else might say they're a 3. That person's 7 might be that person's 3. Not only that, but if I said that I was in pain at a level of 7, and then I said a few hours later, oh, now it's 5, and a few hours after that, oh, now it's 3. The difference between 7 and 5 and 3 may not be the same thing. We have no way of measuring that. All we know is the rank order. That's ordinal data. Okay, grades sometimes are ordinal data, sometimes they're not, right? Because if you got a professor that strictly grades on like a number, or you got 83.5, so you're getting a B minus because you needed 83.5, 83.6 to get a B, right, or something like that. That's kind of like that's almost becomes like numerical data, but for the most part, ordinal data, you know it's order, but you don't really know relative, one level relative to another level, how if they're different or the same. And usually you can't really measure it that easily. That's our main focus tonight. We're interested in what is data, what kind of data do we normally work with. Okay, now nominal data, one of the most common kinds of data that we work with is binary data. Bi means two, right? So classic is male and female. Now, a lot of times what we're going to be doing is we're going to be coding data. We're going to be working with data on computers. Computers are remarkably smart and remarkably dumb. If we were to, say, identify a subject as being male, right, and we typed it M-A-L-E lowercase, and we then typed it up for the next person as M-A-L-E uppercase, it might not recognize that as being the same. So a lot of times what we'll do with data, particularly binary data, is we'll code the data. We'll say, oh, 0 means male, 1 means female. 0 means alive, 1 means dead. So that when we're inputting the data or collecting the data, we have a common reference that the computer is going to understand as that means this. So I don't have to worry about whether somebody misspells it or puts a space into it or capitalizes or not capitalizes it. It's going to make it harder for me to get it wrong. Okay, and also it's easier, right? You type it in one number instead of like, an entire word. Okay, categorical data. Okay, blood types. You could also categorize that as numbers 0 through 4 for the different blood types and so on and so forth. Blood types are categories, right? One blood type is not better than another blood type, right? So they're just categories or nominal data. Okay, we describe them as numbers sometimes, but the numbers only are used as identifiers. So it's easy to confuse that, right? So even though I might say 0 is male, when you see a list of data, you'll see zeros and ones. It's not discrete numerical data. It's actually nominal or categorical data. But sometimes 0 and 1 means something. It might mean the number of siblings you have. No siblings, one sibling. Okay, ordinal, ordered data, ranked data, performance scale. Okay, disabled, fully active, and so on and so forth. Now we don't know what like this is kind of like somebody has to make a judgment. Can do light work, can't do work. Is ambulatory more than 50% of the time. So they make a judgment what ambulatory means, and so on and so forth. So the relative, it's impossible to really say that the difference between 3 and 2 is different than the difference between 1 and 0, but we know that 1 and 0 are better than 3, are better than 4, and so on and so forth. Okay, order is important. The magnitude of the number is not important. The order is important. Okay, that tells us that it doesn't matter if the best is 0 or the best is 4. Okay, let's see. Ordinal data. Number of deaths for leading causes in heart disease. Well, this is just a list of the deaths, causes of deaths in 2010 in the United States. Heart disease is the largest cause of death. Cancer the second, so on and so forth. So that list gives us it gives us ordinal data. The actual numbers is numerical data. Okay, discrete data. Okay, this is all, I always have a debate about this, right? Because heart disease, 597,689, I would have called that numerical data, continuous data. Just because it's a big number. Rather, I tend to call, so I'm never going to make you bend your arm into like really making that hard a distinction between continuous numerical and discrete numerical. Aside from the fact, if you want to be safe and if it's an integer, you want to call it uh, 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 discrete, then you can do it for any of these would be discrete because they're all integers. I would have called this numerical, just scalar or numerical data if I had to. Leading causes of death in New York. We're going to be going over that to some degree later on because we're gonna take a look in the coming weeks. We're going to look at the morbidity and mortality report. Okay, let's see, and continuous data. Time. Time can be broken up into an infinite number of segments. Could be minutes, seconds, tenths of seconds, hundreds of seconds. Weight the same way, length the same way. There's a mass. You could break that up into any number of decimal places. So that's clearly continuous data, even if it's like length 10 inches is an integer, but you'd kind of like say to yourself, well, gee, that's really kind of continuous because it could have been 10.1 inches or whatever. Okay, it can be bounded or unbounded. It can go 0 to infinity, or sometimes it's within just a certain range. So now, why are we doing all this? Because we want to know facts about the population. We're going to collect this data. Sometimes it's going to be nominal data. Sometimes it's going to be continuous numerical data. Sometimes it's going to be ordinal data. Why are we collecting all this data? Because we don't care about the people we're collecting the data on. We're going to use that data to make inferences about the population. Okay. Usually, it's not the sample that's the real object here. It's the population. So we're going to collect information and try and figure out what does that mean in terms of what the real population represents. Okay, so now when you have ordinal or nominal data and you want to describe that to someone, you can just tell them, oh, we got 300 redheads and 4 brunettes and so on and so forth. We have 100 males and 200 females and so on and so forth. Well, that's nice to be able to describe, or similarly with ordinal data, that's nice to describe. How would you summarize that for them? One of the ways that you would summarize that for them is something called frequency tables. Basically, just a table that says male and female with a number next to it, 200 females, 300 males, and so on and so forth. That tends to lend itself to graphical displays. What kind of display would you make for that kind of data? If you wanted somebody to be able to see the difference between the number of females and number of males easily. Bar chart, right? Or a column chart, if you want to call it that, right? Frequency tables are often converted into bar charts. Okay, so now, frequency tables, clinical trial. Let's see, 50 people were in treatment group, 50 people were in the control group. Severity among the people that had the condition, 20 were mild, 30 were moderate, 50 were severe. These are categories, right? In the case of severity, that's ordinal. So we organize the data the same way. Graphical displays, we're going to play around with that a little bit. Frequency tables in another form. This form of frequency tables is called a crosstab. In the rows, we have the severity. In the column, we have whether the person's in the treatment group or the control group. So we see all sorts of information about how we've broken up the sample in this study. Okay, a number of ways you can display bar graphs. This is similar to the way you would use a pie chart, right? This is really kind of a pie chart in reality, right? Because you can see that within the treatment group, let's see, within the treatment group, I guess we had almost the same number. We had just slightly more severe people than moderate and mild people. But you could show that in a pie chart also. Discrete and continuous data. That gets a little trickier because it's no longer easy to make a simple frequency table here. Because if I asked everyone's age in days in this class, somebody may be, let me think about this. 10 years would be 3,620 would be 7. Let's say 10,000. First person is 10,342 days. Second person is 11,000. It could very well be that nobody is exactly the same age in days in this class. So I'd wind up with a bar chart with, if we looked at it the same way we would look at nominal data, which is one person in each bar, right? It'd be pretty useless. Right? So a good way to organize that would be to put together ranges, equal sized ranges. Oh, from 10,000 days to 11,000 days. everybody that's between 10,000 and 11,000 is going to go into this bar.
It's 7 o'clock.
Thank you. And everybody that's between 11,000 12,000 is going to go into this one. And we're going to get a chart that's going to look very much like a bar chart, right? This is not a bar chart. What's this thing called? Histogram. What's the difference between a histogram and a bar chart? Well, a histogram, you may notice that each one of these bars is plastered right up against the next one. So that if someone's severity is 37, they might be in this bar. If they're 38, they might be in this bar. If they're 37.5, they might be over here. But they're in one of these bars, and these bars are continuous, right? If somebody's 52 is rated a severity of 52, he's likely to be in this bar. So this is continuous data accumulated into equal-sized groups, right, in a range. That's a histogram. Okay, very different from this, where it's just this person's in treatment, this person's in control. Notice they're not stuck together because they're in one or the other, right? This one is continuous data, decides where they wind up. Very frequently, we're going to find that they form a particular kind of pattern, and in that pattern, most of the results are in the middle, and there's fewer and fewer people that are way to the outside. For instance, in this class, there are going to be a lot of people that I would say in their 20s, late 20s, mid 20s, late 20s, early 30s. There's going to be very few people in here that are 19 or younger, and there's going to be very few people in here that are my age. Probably I'm the only one, right? Sadly, but that's okay. I don't mind. I'm used to being the oldest. So at any rate, but that's a lot of times the way that we see data distributed. That it's amassed around the middle, but then there's fewer and fewer people to the outside. We're going to take advantage of that in quite a few studies later on. Another way we display data is something called a box plot. Okay, in this data, in this box plot, here's a kind of a rough sketch of the distribution of the data that we just saw. Except in here, this box plot is set up so that there's a box in the middle, right, with a little bar right over there, a dark bar in the middle, and then like a dotted line and a couple of things they call feathers over here. There's one feather there, there's one feather there. Okay, what they represent is this box represents half of the population. Half of the population is between here, between about 42 and about 59, right? Let's say. The mean, the average, the middle person is where this bar is. They're about 45, I guess, or something like that, or 50 maybe this is like double. We're going to be using this to describe, as an alternative to describe the way that the data is displayed in histograms very frequently. Okay, so box plot's interesting thing, nothing you need to know about right now. Okay, these are percentiles that are actually recorded there. Since it's the 25th percentile and 75th percentile, that means 50% of the people are between these two. Okay, sometimes you'll see in your textbook, you'll see an exact plotting of data, which is like a number line, and all they do is they put a tick mark everywhere that there's a person that represents that severity. So you can see most of the people are in here, fewer and fewer people to the outside. Okay, and then you see charts that like really get outrageous, and they show, you know, it displayed every way possible.